Ωραία. Λοιπόν, καλησπέρα σε όλους. Είναι το πρώτο διαζώσει σεμινάριο μετά από χρόνια. Είναι το πρώτο, οπότε είμαστε πάρα πολύ χαρούμενοι να σας καλωσορίσουμε όλους εσάς και αυτούς που είναι διαδικτυακά και βέβαια τον ομιλητή μας, τον Άνω του Σαριδάκη από το Εθνικό Αστυνομικό Αθηνών, που είναι ο πρώτος μας ομιλητής, διαζώσεις εννοώ, από κοντά ομιλητής. Ευχαριστούμε πολύ και καλώς ήρθες. Λοιπόν, θα συνεχίσω στα αγγλικά. Sorry, I'll continue in English now. I welcome you all, whoever is also on the online platform. Our speaker today is Dr. Manos Saridakis from the National Observatory of Athens. He's there as a senior researcher since 2019. He obtained his BSc in physics in 1999, and then he got his master's degree from Imperial, I think, from Imperial University College London. And then he got his PhD here at the University of Athens at the Department of Physics, so he's one of us, right? Almost one of us, right? And then he did a lot of postdoctoral research fellowships in various places, at the Institute of Theoretical Physics in Saclay, at the National Tsinghua University of Taiwan, at the National Technical University of Athens from Metsovio. He also worked as a visiting professor at the Institut d'Astrophysique de Paris in 2014, at the Pontificia Universidad Católica Valparaíso in Chile, 2015, and as an assistant professor at the National Technical University of Athens in 2016. He's currently an adjunct professor at the physics department in Baylor University in the US. He's also a professor at the astronomy department of the University of Science and Technology in China since 2018. So he's very, very active, as you can see, all over the world, right? His research interests are in cosmology, relativity, theories of gravity, dark energy, dark matter, inflation. He's already given us a talk a few years back about his work on modified theories of gravity. I would say he also works on computational cosmology, analysis of cosmological data, gravitational waves as well. He has published more than 240 papers, if I'm not mistaken, in refereed journals. He has more than 15,000 or something like that citations. So today, Manos will talk to us about cosmology and gravity in the new era of multi-messenger astronomy. Are we approaching new physics? So Manos, the floor is yours, and thank you very much for accepting our invitation.
Thank you very much for this nice introduction, and thank you very much, of course, for the invitation to be here. It's always a pleasure to give a talk in my department. So, as I can see, many students here, and as Maria told me, I will be introduced, right? We're going to make a journey in cosmology and gravity according to recent observations, because we're living in a new era, and you are the lucky ones that you are living in the century of astrophysics and cosmology. You know, I would say the 20th century was the century of nuclear and particle physics. This is our century, and you are lucky to face all the new things. This is just some bibliography, some keynote reference papers, if you want to read, and a book that we wrote after a course program that we had in gravity and cosmology. So, let us start. Gravity is the most interesting interaction in nature, right? But it's the one that we know less about it. Why? Because you cannot study gravity in the accelerators. If you want to study gravity, you must do cosmology. So the universe is a laboratory to test our gravitational theories, and this is what we're doing. We look at the sky and we try to understand what is the fundamental physics behind that. I will just start from the beginning, just to show you the main picture that I want you to take back home. This is the following. We have theories, we make predictions, we confront them with the data, and at some point, the data and the theories are in contradiction. And this is the point that we need to search for new. We saw that on and on during the whole history. I started, of course, with the big guy, Aristotle, in the ancient world, and we had the Aristotelian Ptolemaic model. Everything is composed by 4 elements: earth, sun, earth, fire, water, earth, and there is a 5th element that comprises the skies. The 5th element, pentusia, quintessence in Latin. However, even back then, we start seeing some contradictions. You see, the planets, because the Earth is not the center of the solar system, so the planets seem to do a reciprocal motion, and we improve our model with the theory of epicycles. You know about this, right? So all the planets are moving around the sun, but they are doing small circles. So this was an effort to save our theory. However, later on, we had the observatories of Essen and Ara, the astronomers, in the Mercator Observatory, and Galileo was the first to do experiments. So although Aristotle thought that all bodies fall with a different speed according to the mass, he was the first to do the experiments and found out that no, gravity acts in the same way in all masses. At the same time, Bracher, Kepler spent 30 years of their lives to understand how the planets move, and this is the first time that we need to go to a paradigm shift. We need to change from geocentrism to heliocentrism. Okay, why? Because the advance of technology made it possible to do observations that we could not do that in the previous time, right? So we had all this data and led us to a paradigm shift. Then we have Newton. So Newton, for the first time, realized that it's the same force that makes Earth fall on Earth and make the planets move around the sun. So the gravity is a universal force. And this is the first time in the human history that we understand that in order to have a model for astronomy, we need to have a theory of gravity, right? So we understood that, and later on, again, the advanced technology made possible to do high-resolution observations. So, 1859, and you said we saw the anomalies in the Mercury's motion. This was in contradiction with Newtonian predictions. So the data were in tension with the theory. And of course, the majority of physicists believe that Newtonian gravity is correct, and somewhere out there, there is an extra planet, a planet that we have not seen, so a dark planet between the sun and Mercury called the Vulcan, Hephaestus. And this planet was causing the anomalies in the Mercury's motion. However, the tension between data and theory was there for 60 years, until, as you know, Einstein in 1915 solved the tension by a paradigm shift, a new theory of gravity, general relativity. But this is something because in the school, when we learn about that, we say, okay, the anomalies in the Mercury motion may Einstein to bring new theory. But this happened after 60 years. So for 60 years, the physicists were living during a tension between theory and observation. Have this in mind. And of course, this is another thing that you are familiar with, Mitchell-Mori experiment about the speed of light. Again, 1887. You know about that, right? So they were expecting the speed of light to change according to the frame, but it was the same. So again, it was there for 20 years until Einstein proposed special relativity. Again, we were living in a tension between data and experiment. And of course, we now know that we have a gravitational theory, general relativity. In this theory, matter tells space-time how to curve, and space-time tells matter how to move. So in this gravitational theory, gravity is geometry. Okay? Let me tell you here that this is not just a theory. General relativity has been verified in many experiments. We're taking into account in the GPS, for instance, in the satellites. So it's a fact. It's reality. Okay? It's not just a theory. And in order to be a little bit more technical, this is the action of the theory. You know from classical mechanics that theories are characterized by an action. So this is the Ricci scalar that quantifies the geometry of space-time, the cosmological constant. This is the matter part of the Lagrangian. By variation, these are the field equations, and this is the energy momentum tensor that determines the distribution of matter. Right? I guess you know that, or if you don't know, you will soon learn that. So this is the standard theory of gravity that we have. Now, let us go back to observations of the 20th century. scaled through the observations of the previous times, but let me show you now. Here, you cannot see that, it's not very well. So at the scale, so we start and we zoom out, right? We look at the universe and we zoom out. At the scale of 100,000 light years, we have the galaxy. At 1 million light years, we have a group of galaxies. Then, if we zoom out, we go to the cluster of galaxies, compact groups of galaxies, gravitationally connected. Then we have a supercluster of galaxies, and from the scale of 1 billion light years and on, the universe looks homogeneous and isotropic. It's the same everywhere, and this is a map of the universe. So if I show you a picture here and here, you cannot understand the difference. This is the starting point of cosmology. We call it the cosmological principle. So we are living in a homogeneous and isotropic universe. We are not at the center of the universe. I know that many people believe that they are the center of the universe, but no, we are living in a random planet, in a random solar system, in a random galaxy, in a random area of the universe. Okay? And actually, this is an indirect result because, strictly speaking, we are doing observations from Earth only. So we know that Earth is isotropic observation point. So either we're living in the only isotropic point in an anisotropic universe, or all points of the universe are isotropic points. So according to the famous theorem, the universe is also homogeneous. So have this in mind, because we are going to use this in order to describe the universe. Now, observation number 2. The universe expands. And this observation was made by the best basketball player of the University of Chicago, published here, that he noticed that all galaxies seem to move away from Earth, and actually, the further they are, the fastest they move away from us. Okay? And so this is the speed, this is the distance, and this is the Hubble constant. So Hubble constant determines how fast the universe expands. Okay? So the further one galaxy is, the faster to move away from us. However, I want you to understand, it's not that we are the center of the universe and all the other galaxies are moving away from us. Every galaxy is moving away from every galaxy. And actually, this is what we're calling that the space-time itself expands. How we are measuring speed, by the way? How can I see that the galaxy is moving away from us? Of course, I don't see it becoming smaller and smaller. The time scales are huge. We understand it from the Doppler effect. You are all familiar with that. So if I have a moving source of electromagnetic radiation, the wavelength of the photons changes, right? And by the way, what did you just say? In order to do cosmology, so in order to be able to observe the large scales, we need to understand the small scale physics. We need to understand electromagnetism in order to be able to measure the redshift. So in order to find all this. And this goes on and on. The same happened later on with neutrinos and gamma rays and everything. We need to understand the microphysics in order to be able to do astrophysics and cosmology. So if the universe expands, what happened back in time? So we go back and back in time. Obviously, all the galaxies were related to a super dense and super hot primordial atom. And actually, if you put down the numbers, you find out that this happens around 40 billion years ago. So something happened there. All matter that we see now was related in one point. And actually, Alpert, Bethe, and Gamow in the late 40s, they established the Big Bang theory. The name Big Bang theory came from Hoyle, who was an opponent of the theory. He tried to make laugh of the theory. He said, come on, these are ridiculous. This would demand for a Big Bang. And that's why he named the theory, he was hated. So this theory has two important predictions. First of all, since the initial universe is very hot, we had, of course, nuclear reactions, right? We are very hot, and all the standard model of particle physics get involved there. So we understand that nucleosynthesis happened at this primordial state. Not only at the center of the stars, because we know that inside the stars, we have the transformation of hydrogen to helium, right? However, The largest part of that happened in the first 3 minutes of the universe. And if you put down the numbers, this is what we get. And the second most important prediction is the following. Again, due to the nuclear reactions of the early universe, so we have proton and neutrons forming helium, we have the creation of a huge amount of radiation. So many very energetic photons. So these photons have that wavelength over there, but since the universe expands and cools down, their wavelengths expand. So their temperature and their energy falls. So there was a moment around 380,000 years after the Big Bang where the photons had reduced energy and they could not ionize the atoms anymore. So before that, if you had a proton and an electron, and you had the formation of the hydrogen atom, then a high energetic photon would come and destroy that. So the universe was in the form of a plasma. However, after this threshold, the photons do not have the energy to ionize the atom. So atoms are formed and photons travel in a free. So the universe becomes transparent. That's why we call this era the recombination. Okay? So what is the prediction of all this? That we should have a huge amount of photons coming from everywhere. And if you put again down the numbers, because the universe continues to expand. So these photons that propagate in a free way after the recombination, today they will follow a black body radiation with an average temperature of 2.7 Kelvin degrees. So the prediction is that in every direction in the sky, we should get this microwave electromagnetic radiation. Indeed, in 1965, Penzias and Wilson were trying to measure something else. They were building an antenna, but they accidentally found that this is true. We get photons from every direction in the sky. This is the famous isotropic cosmic microwave background radiation. So this is the echo of the Big Bang, in a sense. So Big Bang theory is fantastic. It can explain many things, but it has 3 fundamental problems. The first is the horizon problem. Why the universe in very distant regions is the same, looks the same. So if we look very far away that way, very far away that way, the universe looks the same, it has the same properties. Why? These regions didn't have the time to interact in the past. This is called the horizon or causality problem. The second is the flatness problem, namely why the universe is spatially flat, not space-time flat, it's spatially flat. This would demand an initial, as we say, fine-tuning to put the numbers in a very accurate way. And of course, the monopole problem, that probably you're familiar with that. You know, according to grand unified theories, we predict, according to the quantization of charge, the existence of magnetic monopoles, but we have not seen them. Why? So these are the problems of the theory, and that is why the theory needs to pass a lifting in the beginning of the 80s, where we introduced the phase of inflation in the early years. Now, what is the phase of inflation? It's a mechanism. We don't know exactly what mechanism, but we know that there has been such a mechanism that in the initial phase of the universe, so 10 to the minus 36 seconds after the Big Bang, the universe went through an exponential rapid expansion. So, although inflation had a very small duration, it was enough for the volume of the universe to expand exponentially. So we are living in a tiny region of the whole universe. So the observationally detectable universe, the universe that we see, is only a minor part of the whole universe. So now we solve all the problems. Why? Because this minor part comes from an initial connected, causally connected region. So that's why we have the same physics in the whole universe. Secondly, due to the huge expansion, spatial curvature is 0, like to the planet Earth. It has a radius, but it's huge, so it looks like flat. It's not flat. It looks like flat. The same is for the spatial curvature of the universe. And of course, due to the huge expansion, all the magnetic monopoles were spread in this whole universe. So in our observational part of the universe, our observable universe, as we say, we have statistically around 1. That's why we have not seen that. So this is the idea. This is the whole universe, the Big Bang. This is one tiny part that undergone the inflection here, and now we have the predictions of our universe. So we are getting. Any questions up to now?
Why the universe is huge? Does ever end? I mean, how can we say that?
Okay, first of all, the observable universe is the one that we see. We know the radius, we know everything about that. The question is whether there are things beyond that. And the answer, according to this, is of course yes, because if there were not other parts outside the observable universe would have different properties. Now, the question why there is a universe at all, this is a very interesting fundamental theory. Why exists something and not nothing? And this has to do with quantum gravity that we don't know the answer, but according to our intuition, we are here because of an anomaly in the early time. So an initial quantum fluctuation out of nothing created this anomaly. The universe is a defect, it's an anomaly. Okay, I hope I answered you partially, yes.
Have we ever witnessed quantum fluctuation in
Very good.
experiments?
I will show you later on after very good question. Okay, now let me come to the actually to the end of the 20th century and to the observations that we had back then. First of all, dark energy. We know that we have the supernova explosions. These are very nice objects in astrophysics because we know the physics. So we know how much radiation they emit. Why this is important? So if I have this lamp over there, and if I know how much radiation is emitted from there, and I'm sitting here, and I'm observing the radiation here. So what can I calculate according to the inverse square law? The distance. So supernova are called standard candles because they allow us to determine distance. So speeds are determined due to the Doppler effects, distances at this level according to supernova. So in 1998, Bermuda Smith and Rees observed the following. They saw 50 supernova, and they understood that the supernova explosions look less bright than we expected. So less bright means that the light travel more time to come to us. So it means that the expansion of the universe today is faster than the expansion at the past. So this means that the expansion of the universe is accelerating. You see? And actually, this interesting observation that the expansion of the universe is accelerated was verified by very other independent observations from CMB and baryonic acoustic oscillations. So we now know that around 70% of the energy content of the universe is the source of this acceleration, and we call it dark energy. Energy because it's the form of energy, dark because it does not interact with electromagnetism. So the possible explanation is the cosmological constant. This was a term inserted by Einstein. So when Einstein beat general relativity, people believe that the universe was static. But general relativity is an attractive theory of gravity. So a static configuration should be unstable. It should collapse under its own gravitational interaction. How can we solve that problem? This is what Einstein did. He introduced this term, which is a form of negative pressure, a form of anti-gravity to make the universe stable. However, after the expansion of the universe was found, you don't need that. You don't need a cosmological constant because the universe expands. And of course, in a decelerating way. However, after the supernova things that we understood that the universe expansion is accelerated, we need to put lambda, the cosmological constant, into the game again. Second observation, dark matter. We have two sources of experiments. The first is the galaxy rotation curve. So if I have a galaxy and I'm observing how it rotates, as you know, the mechanics of the rotation is determined by the amount of mass that we have there, right? These are high school calculations. So from the rotation curves that we are observing, we find that there is more mass there that we cannot see. So there is more mass than the stars. And there is a second observation, the collision of clusters of galaxies. And this is the bullet cluster. Again, the mechanics of the collision is determined by the total mass that is there, right? And again, the mechanics of this collision show us that there is more mass there. So we put out the numbers, around 80% of the mass content of the universe is in this form of dark matter. Why dark? Because it does not interact electromagnetically. And this is the distribution of matter and dark matter in the universe, this fractal structure. Of course, every point here is a cluster of galaxies, and this is the observable universe. And we need to explain, of course, that. I'm coming now to your question and the structure of the CMB radiation. Okay, we said that we are expecting a black body CMB radiation coming from everywhere with an average temperature of 2.7. Okay, but after the 90s, technology made it possible to send satellites in the sky and observe CMB structure in a more detailed way. And interestingly enough, what we found was this structure. That of course, the average temperature is 2.7, but there are anisotropies at the level of 10 to the minus 3 or 10 to the minus 4 Kelvin. And this was Kobe satellite, this was WMAP, next decade, and 2000 to 2010, and this was the Planck satellite from 2010 to 2020. You can see clearly the improvement of the revolution, of the resolution. Why you can do that? Because technology made this possible. So here there is a structure. Of course, you cannot understand anything by looking at that. How can we export information from that? By looking at the spectrum. So you calculate the 2-point correlations there, and this is the spectrum of the CMB radiation. So all the information is here and here. And indeed, this gives us information about the underlying cosmological scenario. So the first peak shows us that we are living in the spatially flat universe. And then these peaks give us the amount of baryonic matter and dark matter. Right? For instance, I told you before that 80% of matter is dark matter. How do we know that? From this structure here. I don't want to get into the details, but just to understand that there is information there. Why? Because the CMB radiation, in order to come from the recombination time to today, it travels through the whole universe. So it carries information of the whole universe. And we are sitting here and we're trying to understand what kind of information we can earn. And the question is the following: how can we explain this large-scale structure of the universe? Why we have galaxies here and not here and here? And this is a byproduct of inflation. We need inflation in order to solve all the other problems, but this is the key answer here. We need to have the initial seeds of this, and these were the quantum fluctuations. So in the primordial universe, the quantum fluctuations of the inflaton gave the initial overdense regions in order to play the role of seeds, in order to have the gravitational collapse. So the proof that there was a phase where quantum fluctuations were dominant is this structure. Otherwise, the universe would be different. So this is the summary of observations. Every theory of gravity needs to be able to predict all this. And this is the composition of the cosmos. You know that heavy elements like Earth, 0.03%, neutrinos, 0.5%, stars, 0.5%. So all the stars have just 0.5% of the universe, free hydrogen and helium, 4%. So this 5% is what we know. The rest, 95%, is what we don't know. And from this, 25% is dark matter and 70% dark matter. So this is what we need to understand. Any questions? Okay, how can we describe the universe? Of course, we need a theory of gravity, and we have it, general relativity. So general relativity describes the four-dimensional universe. Let me be just a little bit more qualitative. So this is the metric according to #1 principle of cosmology, the cosmological principle. The universe is homogeneous and isotropic. So this means that this four-dimensional space-time depends on your time, and this is the scale factor. Just to understand, the scale factor shows how big is the universe, right? So this is an increasing function in time. The universe expands. And this K here determines the spatial, the three-dimensional curvature, which can be closed, open, or flat. You know about this, I guess, right? So the triangle, if you draw a triangle in a flat space, the sum is 180 degrees. Here is different. So this has to do with the geometry of the three-dimensional space-time. The four-dimensional, so the whole space-time is non-flat, of course. This is the idea. So this is the metric, and these are the basic equations. So this is something that I want you to take back home. This is the beginning of cosmology, and this is something that we teach to the students of all cosmology classes. The Friedman equation. So the Friedman equation, which is the essence of GR, of Einstein's theory of gravity, on the left-hand side, we have the geometry of space. And on the right-hand side, we have matter. So the geometry, this is the Hubble function, which is A dot over A. So the Hubble function, as I told you, tells you how fast the universe is. So H is A dot over A. Okay? So this is geometry of the universe, and this is just what I have inside the universe. Matter. In what sense? In the hydrodynamical sense. So I assume that this is a perfect fluid. So I don't care about the details of matter. I have zoomed out. So I see just a fluid of matter, and the particles of this fluid are the galaxies, or the clusters of galaxies. So this fluid has a density and a pressure. And I have the dark matter fluid, the baryonic fluid, and the radiation fluid. So these are the three ingredients of the universe with the pressures. And of course, this lambda is the source of acceleration of the universe, the cosmological constant. So this model is called lambda CDM, lambda CDM from cold dark matter. This is the standard model of cosmology. So we will end here. And actually, just to let you know, it's interesting that cosmology is the science with the highest amount of agreement between scientists. Everyone in cosmology agrees with that, but this is the base that you start. You cannot find this consensus in other sciences. So these are the equations that determine the evolution of the universe. I need to add the inflationary states at the beginning, and there is another guy called the equation of state parameter of the fluids. So this has nothing to do with cosmology. This depends on the fluid. For instance, matter has zero pressure. So W, which is pressure over energy density, is zero. Radiation has W 1/3. So you see the equation of state, as we know from school, determines the state, so the internal properties of the fluid. Now, of course, we need to explain this. And in the early, now I will just sketch you some things. In the early universe, it's more complicated. We need to solve the Boltzmann equation between all the ingredients that we have. And this is what we are doing. And of course, then you go to the Legendre polynomials, and you predict this CMB structure. This is now what I want you to learn. This is a structure of the cosmic microwave radiation that we predict according to some theories. I told you what is the CMB radiation. It has some anisotropies, and we make the spectrum of it. Now, you can see how the spectrum is sensitive to the quantities of our theory. For instance, according to spatial curvature, you can see that according to spatial curvature, the spectrum moves from left to right. So this is how we see the spectrum. We see this thing. We see this guy. And we try to understand from here the important quantities. How we are doing that? Because all these quantities will give a different spectrum. So curvature determines the first peak. Dark energy changes this low L level. And here we have the baryons and matter in general. So now we know how our theories determine the spectrum. So in the inverse way, we can extract the parameters of the theory from the spectrum. And the second thing is the large scale structure, because now we have a high resolution map of the galaxies. So we know our universe, and of course the universe changes, and we have the initial conditions from inflation. This was the initial seeds, and then as time passes, we have the creation of the large scale structure of the universe. And this is the spectrum that we observe. So why the galaxies are in the distance it is now and not in a different distance? So this is the important question. Why the galaxies are here and here, not here and there? You need to explain that. And indeed, this is what we are doing in our models. Now, here, so this is in the past, it's red in the past, and this is today. And this is the map of the universe. Here, these plots are in a universe without dark energy, and these plots are in a universe, this is with dark energy, and this is without dark energy. So the universe is different. So we are looking at the universe, and we know that we see this picture and not this picture. That is why we understand that we have 70% of dark energy. So you see, we are now in a level that astrophysics and cosmology are accurate science. We have a huge amount of data, and we exploit them. And from this data, you can do many, many things. So according to the questions, we believe that there are huge areas outside the observable universe, because if they didn't exist, our universe would not look like that. We will be living in a different universe. So this is lambda CDM, the standard model of cosmology. Of course, there are some open issues. It's a fantastic model. It can explain the universe from the very early times up to today, but there are some issues. The first is a theoretical one, that general relativity is a non-renormalizable theory. So it cannot get quantized according to the techniques that we have up to now. The second is the cosmological constant itself. Okay, we need that, but if we go to calculate its value, we found that the value is 120 orders of magnitude smaller than our calculations. This is the worst error in not only the history of physics as we used to get, but the whole history, right? It's a huge error. And of course, we don't have a model of inflation, but this is the important thing that I want you to sketch some things. We have some tension now with the data, some important tensions. And of course, there are other higher scale problems like the missing galaxy satellites problem or the cosmic core problems. So there are small issues, but don't underestimate them. Don't hide them under the carpet. From these tensions between the data and predictions is where new physics is hidden. So I will just mention your two tensions, which are really important. The first is the H0 tension. H is the Hubble function, and H0 is the value of the Hubble function today. So we have two ways to calculate H0. The first is from all these cosmological observations from the CMB, we estimate H0, and we find 67 megapascal per second, kilometers per second per megapascal. However, there is a completely independent way to calculate H0 from local observations. So we are looking at the Cepheid galaxies. Anyway, this is astrophysics, but we can calculate H0 without caring about the cosmological model. And there is a contradiction between them. The second way gives us 72, so we are 5 sigmas away. And there are many, many, many independent groups and many other observational data sets that give us this tension. So the H0 value that our theory, this lambda CDM model of cosmology predicts, is in contradiction with the one that we observe in the local universe. So this means, just to tell you, that the universe expands faster than we expect. And of course, in order to solve this tension, okay, if it's not systematic, perhaps we are doing something wrong. However, there are many good people, and we got also a huge grant in a new cost action, and with NASA and ESA, that we are trying to solve this tension, and we believe that there is something there. This is why I told you in the beginning, we have tension between predictions and the data. Of course, there is a possibility that we are doing some stupid mistake, but there is a possibility that inside here there is new physics, like we had with anomalies in the Mercury's motion and with Kepler and all the others. So, of course, in order to solve that, either you need to change the early universe physics, there are new particles, for instance, or the neutrinos are not free, or you need to change the gravitational theory. I have to move. How much time do I have?
About 15 minutes.
Okay.
Yeah, but we can take longer if you want.
Okay. And the second tension has to do with the large-scale structure of the universe. Again, we observe the galaxy distribution, and we can calculate their spectrum. What we see, and we have two ways to do that, either assuming all this lambda CDM cosmological paradigm and estimate that, or by measuring one by one the galaxies. So what this data tell us is that we observe less clustering than what we expect. So matter clusters in a weaker way compared to our predictions. So this is the sigma 8 tension, but the H naught tension is much more severe. And again, in order to solve this tension, you need either to change something in the early universe or assume other things, including modified gravity. I will come to that. So this is the knowledge of physics that we have. The standard model of particle physics and general relativity for gravity. And this model was completed by the discovery of the Higgs boson. So the question is, can this knowledge of physics explain on this? And the answer is most probably no. We need new physics for inflation. And that's why I spent you 5 minutes to convince you that we need inflation. If we agree that we need inflation, we need new physics. What is the mechanism that drives inflation? We need new physics for dark matter. This is almost certain. Probably we need more physics for dark energy. These are the theories of dark matter. I don't have time to talk on this. And let me come now to the other choice, that we need to modify gravity. Now, if we add a new particle, which is one way, you can find solutions like the quintessence field. So this is Aristotle's revenge. There is another particle beyond standard particles, standard model of particle physics, and this drives the universe acceleration. I don't have time to get into the details. The other way is to change gravity. And this is what we are doing, and you can find hundreds of new theories of gravity in the literature. So the idea is, again, in the same way that Einstein modified Newton, so in order to solve the tensions with the data, we went to a new theory of gravity, which has, of course, Newtonian gravity as a limit, but in general is a different theory. We tried to make new theories of gravity that have, of course, general relativity as a limit, but in general, they are richer theories with more degrees of freedom that can drive the universe acceleration and everything and can explain the data. So there are many ways to do that. The first is to go to higher dimensions, as we know in string theory or brainwork models. GR is a 4-dimensional theory. So if you go to higher dimensions, this is modified gravity. You can introduce new scalar vector tensor degrees of freedom. You can introduce more complicated geometries, including torsion and everything. Or you can even think of more radical modifications, like a statistical parameter theory, for instance. As you know, just to give you an example, temperature does not exist in the macrophysics, in the fundamental world. It's a statistical effect which appears according to the increase of the complexity of the system. So there are some people who say, okay, perhaps the same things with gravity. Gravity does not exist at the fundamental level, but it arises statistically as we go higher. Fundamental level is the Planck scale, right? 10 to the minus 43. But then it arises. So these are more fundamental modifications of gravity. So what we are doing is the following. We build theories of gravity and we make predictions for the universe. We confront the predictions with the data, and if we cannot describe the data, the theories are excluded. Otherwise, these are called viable theories. So the idea is the following. You take any theory you want, you calculate the Friedman equations, and here you have the extra terms that you call them dark energy. So you have 1,000 theories, and each theory has a different effective dark energy here. Then you predict the Hubble function, and you go to the data, and you confront the theory with the data. This is how we play the game at the background level, and this is the thermal history of the universe. As you might know, so in the early universe, radiation was dominant. Then we had the matter era, where matter sector was dominant. And in the recent cosmological past, we have the accelerated, the dark energy rate. So this is the basic requirement. And just to give you a hint about perturbation theory, because it's a bit complicated. Okay, if we have the general picture of the universe, we are living in a homogeneous anisotropic universe. It evolves, it expands in an accelerated way, etc. However, when we start zooming in, we see the details of the universe. So the universe at smaller scales is not completely homogeneous and isotropic because we have the large scale structure of the universe. So how you do that? You make a perturbation theory, as you probably know from classical mechanics or from quantum mechanics. So you perturb the system, you deviate from homogeneity and isotropy, and you deviate also from homogeneity in the matter distribution. So this guy there, delta, is delta rho over rho, is the matter of a density. This is zero in a homogeneous and isotropic universe. It is non-zero in the real universe. How do you measure that? We measure the galaxies and we calculate that. But this is related to gravity. Gravity tells us how fast the universe should cluster. So with perturbation data, we're calculating and we study the universe at a more detailed level. Let me just to show you, for instance, this is the famous Ego-Bar gravity. So instead of general relativity, we go to a modified gravity in which the Lagrangian is a function of the Ritz scalar. So this theory, don't pay attention to the details, we obtain modified Friedman equations. So we obtain a different prediction for the universe. So we go to see the data. And if the data tell us that this is a viable theory, we keep it. Otherwise we kill it. And let me, in the last 10 minutes, I'm going to skip some things, some modifications of gravity, and I want to go to the revolution that happened the last 7 years. And this is the beginning of a new era that we call the multi-messenger era. Why? Because this is the first time that we observe gravitational. What are the gravitational waves? These were predicted by Einstein in 1915, and actually they were discovered exactly 100 years later. So these are waves of space-time. If you move in an asymmetric way, as I'm doing here, you emit gravitational waves. Of course, these are tiny. However, if we have some very heavy objects, the gravitational waves emitted there will be detected. And what are the heaviest bodies that you know in the universe? Black holes. So what we saw in 1915 were the merger of two black holes. So you have two black holes in the system rotating around each other. They merge, they form one black hole, and in this procedure, you have the creation of a gravitational wave. How do we detect that? We have an interferometer. So this is 4 kilometers, the 200 of the interferometer, and we have a laser beam going up and down there with mirrors and of course in vacuum and everything, in low temperature. So the laser beam has a structure, all the deflections and everything. Now, if a gravitational wave passes through Earth, the Earth shakes a little bit. So the length of this hand of the interferometer changes. So the picture of this laser motion and all these phenomena that we observe changes. So we understood that the gravitational wave passed through that. By the way, if a gravitational wave passes through the Earth, the change in the length of this interferometer is 10 to the minus 18 meters. So it's smaller than the, you know, not only the atom, but also the nucleus of the atom. However, we are smart enough to be able to measure that. But of course, this small change in the length could be noise. I mean, if one guy in this cafeteria put a bottle on a desk, the noise will make such a change. Yes, this is correct. However, if you look at the same change in Louisiana and Washington, so in the LIGO experiment, and in Virgo in Italy, so in 3 detectors in different places around the world, it's not a noise, it's a gravitational wave. So this is what happened in 2015. We have two black holes with 36 solar masses and 29 solar masses. So they were rotating around each other, and they merge and they form one black hole. So this duration is for half a second. And we have the creation of one black hole with 62 solar masses and the gravitational wave. By the way, what do you observe? We had 36 solar masses before and 29 solar masses, so 65 solar masses before the event and 62 solar masses in the final black hole. So what happened to the 3 solar masses that are missing? They transform to the energy of the gravitational wave. So in half a second, 3 solar masses were transformed from mass to the energy of the gravitational wave. The power of this event is equal to 50,000 times the power of all stars of the universe. Just to understand how violent these effects are, and that's why, of course, a gravitational wave makes the whole universe ring like a bell. However, the revolution came 2 years later when we saw the gravitational waves from 2 neutron star mergers. So we have 2 neutron stars instead of black holes, and we had the rotation and then the merger, and we have the formation of a gravitational wave. However, at the same time, because now these are not black holes, these are neutron stars, we had the emission of gamma rays. So this is what we're calling multi-messenger astronomy. At the same time, we observe the gravitational wave through the gravitational window and the gamma rays through the standard electromagnetic window. Why this is revolutionary? Because for the first time, we can look at the universe from a different window. And just to let you know, if you have black hole mergers, so gravitational waves from black holes, in order to make calculations, you need a gravitational theory. So you assume general relativity. However, in a multi-messenger event, you can use the electromagnetic physics to calculate things independently of the underlying theory of gravity. So you can use this data to test the underlying theory of gravity, and that's why this is a new and huge tool. Just to give you one example, according to one event, this event, we observe that the gamma rays arrive in the Earth at the same moment, 1 second after the gravitational waves. So this shows us that the gravitational waves propagate at the speed of light. And indeed, the ratio of the speed comparing to the light speed is 10 to the minus 15. So with just one event, we were able to kill many theories of gravity. Why? Because many theories of gravity predict that gravitational waves move at a different speed. So just one event killed many theories that had passed all the other tests. That's why it's important to do physics from a different window. And in the last 5 minutes, just to show you, of course, gravitational waves are described by a wave equation. And these are the tensor perturbations. These are the gravitational waves. So this is the second derivative. Now, in any theory of gravity, we obtain two corrections comparing to GR. So one affects the amplitude and the other one affects the phase. So what you are doing is to predict the gravitational waves properties in your theory. One other smoking gun, as we say, is the extra polarization modes. You know what's the polarization of a wave in electromagnetism. So gravitational waves also, it's a bit more complicated because now it's a spin-2 field. We have two polarizations, but in a different theory of gravity, we have extra polarization. So if you see one of these, you know that general relativity has to be modified. And this is what we are doing in our groups. You take theories, and in our research, you take theories, you calculate the gravitational wave properties, and you confront with the data. And then you try to understand whether you have new physics or not. These are how the gravitational wave solutions look like in this kind of theories. And actually, this is a cartoon, because you know there are hundreds of theories in the literature, and we have to do all this analysis one by one. And there are theories that we expect to be sensitive, for instance, to the gravitational wave speed, the data, of the dispersion relation, of the damping, or the oscillations. So there is a huge work for the community in the next 10 years that we need to make in all these theories the gravitational wave calculations. So for the moment, we have seen around 60 gravitational wave events. There is an application that you can put in your phone and get a beam when you have a new event. And we are trying to understand what's going on, but we expect, according to the near future, either on Earth or in space, detectors, many thousands of events. So let me summarize. We have a huge amount of data because we are living in the century of astrophysics and cosmology, which allow us to study the universe in a high resolution way. And we have a very, very successful cosmological model, lambda CDM model. So we are living in an expanding and accelerating universe that inside it we have baryonic matter, dark matter, radiation, and the source of acceleration. We are using many data sets in order to test it. There are some problems in that model, and I told you about two tensions. The first tension is severe. We believe that we are touching something there. It's very serious, and that's why all the big collaborations in the world are looking towards the solution of this tension. And gravitational wave discovery and multi-messenger astronomy opens a new window. We can see at the universe for the first time from a different window, and that's why it's a revolutionary tool. So let me end here that we are doing observations the last 5,000 years. And of course, as you know, this is the Antikythera mechanism that we have in National Observatory of Athens, and we are doing 500 years of organized observations. For the first time that Galileo saw his telescope on the sky. Now, think of how the universe picture changed during this 500 years. What was the picture of the universe that we had in 1600s and what is today? So we are doing gravitational waves observations with the interferometers for only 6 years. So you can only understand how the picture of the universe will change in 400 years from now. And let me end with the big guy. This was written, you know, each time that the people could not understand something, they invented a peculiar fluid, that there is a fluid out of nowhere that does the job. So this was the discussion about the phlogiston fluid. So the statement goes like that. They are the ones that invent occult, strange fluids to understand the laws of nature. So each time they don't understand something, they assume that there is a fluid that does the job. They come to conclusions, but sooner or later, they run into dreams and chimeras, neglecting the true constitutions of things. However, there are those that, from the simplest observation of nature, they reproduce new forces. This is what Newton did to the theory of gravity, and this is what we believe we should do today and try to understand a new force so a modified theory of gravity. So thank you very much.
Thank you very much. Questions?
You don't have questions, it means either you didn't understand anything or you understand everything. So yeah, come on, feel free to ask.
Yeah.
Despina, I cannot hear you. I guess.
But we can hear you, Harris, we can all hear you, so you can.
Okay, okay. Mano, thank you very much for your great talk. I would like to give us the general consensus at this time. Is there some trend in at least the majority of cosmologists about what is the reason of this discrepancy, or you have small communities of cosmologists, each one have his own theory and tries to show and insist that this is the right explanation. And also, I would like to comment on: do you think that there are observational things that we may have neglected that may have led to this discrepancy, or everything is clear and we believe in them?
Very good questions, Harris. Okay, for the first one, because this is a hot subject, and also we organize a conference in September on these things. Well, there are, for the moment, there are 100 solutions of the tension. So this means that there is no solution. And actually, there is not a consensus. The modified gravity groups believe that we should look for a modified theory of gravity. Other people believe that astrophysics should change. Other people believe that there are systematics. So each group has, for the moment, the perfect solution, but in their own means. So yes, there is no consensus. Now, whether it's systematics or we have neglect something, it seems progressively that this is not the case. I mean, we have checked everything. Many independent groups have checked things. We have independent measurements. It's not only the CFITs. For instance, from gravitational waves, we can estimate the H naught. So it seems that there is not an error in the observation. The observation seems to be correct. That's why in LISA, I mean, as you know, we joined LISA in order to offer theoretical predictions on various effects, and NASA also. So these guys seem to believe that there is something else that it's worthy to study.
Thank you, Mano.
All right.
The theories that have passed the tests, let's say, do they have different predictions for the corrections in different scales? For example, in the middle scales that, locally, in the large scale, in the intermediate scale.
Very good. Yes, the answer is yes. They have different, in general, they have different predictions in different scales. So this is a problem because some of them solve some problems in some scales, but they spoil things in other scales. It's very, very difficult to find a theory that modifies in a successful way the standard law, as you say. Because you fix problems in one way and you spoil things the other way.
Is there any theory, modified theory that sort of doesn't destroy, works in all scales at this point?
I would say no. Although this is not a good answer, I would say no. This is the interesting thing, that we know that general relativity is not enough, but we don't know, we don't have the answer. What will be the theory that will replace that?
You talked about the universe without dark energy. How can we predict such that?
No, these are not data, these are simulations. So we are doing simulation because the universe has that energy. So these are the data, but we are doing simulations how the universe would look like if we didn't have, for instance, dark energy or dark matter. And we compare that picture with the real data. We know because we have the theories that we believe that are correct, and we are making simulations. And that is why we know how the universe would look like. As you know, as we previously say, that there are known unknowns and unknowns. Dark matter and dark energy are known unknowns. So we know that they are there, but we don't know what it is. Of course, there could be the case that there are things that we completely miss. We don't know. But for the moment, we are doing simulations in that way.
Could there also be some kind of anisotropy in the universe that has not been measured, or that isotropy is a fair approximation that's not exactly correct, and some of the observed problems can be accounted for by some kind of field of anisotropy or non-homogeneity or something like that?
Very good question. The answer is yes, there were many models predicting that the universe is not isotropic. For example, we are living in a void of the universe. That's why we feel that there is an acceleration. So the acceleration is a local effect. But in that scale, the answer is no. Now we have a huge amount of data, and if you start making calculations, a model like that cannot predict the observed behavior. However, let me tell you that there is a discussion. One of the tensions, I didn't have the time to talk about you, is the possible dipole anisotropy. That there seems to be a dipole anisotropy in the CMB data. It's not a standard consensus, but many people think that, okay, perhaps this is another tension that we need to find a solution. So the answer is, in general, the universe is homogeneous and isotropic on large scales. However, there could be small anisotropic deviations.
You talked about zooming out from our galaxy and see vast scale. Why do we stop the universe? How do we know we can't zoom out anymore?
Good question. Very good question. This is the definition of the observable universe. Why there is this horizon, as we say, this is called the cosmological event horizon, because we are living in an expanding universe, so there is a maximum distance that beyond that we will never have the chance to interact with, because light will need infinite time to come from there to us. So we are bounded inside this cosmological horizon, and this marks the observable universe.
Some slides earlier, you mentioned that the 3 solar masses or worth of masses lost in the final stages of the merge. How do we know that these 3 solar masses aren't lost exactly, or they are not exactly 3, because there were error bars?
Yeah, there were error bars. First of all, you are asking how we calculate that. First of all, why 36 and 25? From the gravitational wave structure, so from the event, the signal that we saw. So this picture here has the information. So the frequency here give us the. So from this picture, assuming general relativity, we understand that we have 36 and 29. Because if the masses were different, this event would look different. However, I repeat that this is assuming general relativity. If there is another theory, all this will change. However, of course, we expect this theoretically, that there should be an energy transfer from the masses to the gravitational wave, because the gravitational wave has energy.
However, my question was, how do we know it's 3 solar masses? It might not be exactly 3 solar masses.
Okay, it's 3 plus or minus something, but we know the difference because we know the mass of the final black hole and the initial ones.
And the second part of the question. So there is another way that a black hole can lose energy, apart from its Hawking radiation.
Okay, yes, the Hawking radiation is of course another way, but it's very, very, very slow. It's very, very slow. You need time scales, huge time scales, in order for a black hole of this mass to evaporate. Small black holes, like the primordial black holes that we might have, evaporate, of course, in other timescales. But black holes like that, you should wait for a long time to be evaporated due to cosmic radiation.
If I recall correctly, when LIGO started observing, there were many more observed events of very massive mergers than initially predicted that there would be. So this means that there are many more so massive objects that predicted to account of some of the proposed dark matter or something like that. Like, if there are so many objects, like, could there be even more?
Good, very good. Okay, all these interesting questions are the ones that multi-messenger astronomy will show us the answer. Yes, there seems to be many black holes of various ranges, and even in the future with ELISA and other observations, we're going to understand earlier. We are going to go up to redshift of 100 to see what happened earlier and how many black holes were there. So the answer is yes. There seems to be strange and interesting things, and that's why we're making theories. For instance, now we start touching the primordial black holes. So many of these black holes, probably they were created in the primordial universe. Probably or not. We don't know. That's why we need to use the data in order to understand what's going on.
So you mentioned that with this multi-messenger event, the GW17 something, you were able to discard many theories, alternative theories of gravity, based on the measurement of the speed of light. And then you mentioned polarization of gravitational waves as another theory, diagnostics. So what are the measurements you need from gravitational waves to exclude alternative theories besides these two?
To exclude the alternative theories or to exclude GR?
To exclude.
Yeah, to do physics. Anyway,
Yeah.
there are many things. That's why I sketched this in this cartoon. So because all these are theories, and all these make different predictions for the speed, for the dispersion relation, for the damping, from the oscillations, and for the polarizations. So for the moment, for instance, we have seen only two polarizations. So this is GR. However, in the future, these are the things of the gravitational wave that we need to see in order to be able to do the analysis. So if you start seeing anomalies in the dispersion of the gravitational wave that do not agree with GR, then this could be a smoking gun or other things like that.
But do you need these events to take place in large distances, for instance, to measure GW dispersion, or?
You need, yeah, in principle, you need to go to high redshift or to low redshift, and you need to go to other frequencies as well, because for the moment, LIGO and Virgo these are the frequencies. Okay, I don't want to get into the details, but for instance, in LISA, we are going to reach to other frequencies, and then we start to have statistics.
Get a dispersion.
What, sorry?
Get a dispersion.
Yes. I mean, so in general, we need to cover redshift space and frequency space and intensity space. But this will happen in the near future. I mean, in the next 10, 20 years, we will have thousands of events in this kind of stuff. So that's why it's very, very interesting.
Could it be that we think that the universe is isotropic because we see 2 points exactly opposite of each other, that they're the same? Could it be because of the curvature of space-time, or because we can't actually understand more dimensions? I don't know if it makes sense.
It may, okay, for the moment, leave the higher dimensions aside. Now, the other things, it's just mathematics. If you go backwards in times, these opposite regions didn't belong to causally connected area. So it's impossible to have the same properties. They should have been in the same causally connected region. That's why we need inflation. Now, if there are other dimensions, there are many models, of course, and then, of course, things change. However, higher dimensions, then you need to see how you can detect them. For instance, in CERN, they are looking for them. So it's a different story. But in principle, yes, you could have solutions there. But these are, today I just described the standard things.
If I understood it correctly, when you said that we measure the gravitational waves, we got to the conclusion that the speed of the waves is equal to the speed of light. So we discovered some modified versions of gravity, correct?
Yes.
Okay, but the answer of another question, you said that assume general relativity is correct, we get the conclusion that it's paradoxical.
No, exactly. This is what I want to say. If you see only black holes, black hole mergers, you need to assume general relativity. If you are doing multi-messenger things, so you have two neutron stars, then you understand things about the electromagnetic part of the event of the gamma rays, and then you find out information about gravity without assuming GR. So this measurement of this gravitational wave speed was a measurement. You didn't assume general relativity because you saw the gravitational waves arriving at the same time with the photons. Okay, so it's both of them.
The magnetic monopoles in the star. So how would we detect these monopoles?
Good. Okay, if these monopoles are particles, so there are particles, and you could detect some of them. And there is a big discussion how we are detecting defects in the universe. So there are many ways. It's like asking, I mean, how do you detect the proton bursts? You could detect it in many interactions, in many observations, if they exist.
One more question? Maybe we can ask if there are any questions from there. No? We can see. Thank our speaker again. Very much.
The cookies. Yeah, this is what.
Maybe this is